Hello and welcome back to another homework video. So today I'm going to start by deriving an expression for the overall thermal resistance of a pipe wrapped in insulation. So that's what I have drawn here. So this is going to be the pipe and then it's wrapped in insulation. And I also have the equation that we derived in the last video when we were finding what the thermal resistance was. And so I can label that here, that this section specifically is the thermal resistance. And this is specifically by conduction. Okay, and then for this example, it's a pipe wrapped in insulation, and then the insulation is going to be in contact with, let's just say, the air. So we have to find the thermal resistance by convection as well for this problem. So we can say, or we can start with the heat flux by convection is equal to the heat transfer coefficient times the surface area times the change in temperature. And then if we wanted to get the resistance section by itself, that's just this part here, because we can manipulate the equation to be to have the delta T on one side and the Q on the other to make it look like this equation up here. So this will be the change in temperature is equal to the heat flux by convection, I'll just specify it, times 1 over the heat transfer coefficient times the surface area. And then this part here represents the thermal resistance by convection. And we can use this to find the overall thermal resistance for this question. And so to find the overall thermal resistance, that can be R total. This is going to be similar to how you would do an overall resistance for resistors in series. We're going to be doing the same thing, but with the thermal resistance instead. I did this in previous videos as well. And so the total resistance, you're just adding up the thermal resistance by conduction and convection. It's just going to be R conduction plus R convection, which we just did up here. I'll make that green. And that's the orange. Okay. So now we can plug some values in. So we have that the total resistance is equal to the resistance by conduction. So that's going to be the natural log of the radius 2 over the radius 1. And this is all going to be divided by the negative thermal conductivity times 2 pi times the height. And then if we look at the example, let's assume that the heat inside the pipe is going to be at a higher temperature than at the outside. So the heat transfer is going to be from high to low. And this is in the same direction as your distance, like what direction you're expanding out or your radius. So because they're in the same direction, we don't need this negative sign. So we can take the negative off of the thermal conductivity. There. And then the height of the cylinder, I can draw it this way. So the height of the cylinder, I'm just going to call it the length, or L, because we have an H over here as well. So let's change this to L. And then we want to add the thermal resistance by convection, and that's going to be 1 over the heat transfer coefficient times the area, which is 2 pi r times L. So this is the equation to get the total thermal resistance for this scenario. So now with this equation, we can take the second derivative of it, and it'll tell us what the optimal amount of insulation to have is for this example. And it'll also tell us what the critical point is to see what the minimum or the maximum amount of insulation we should have for this example. So let's take the first derivative. So it's going to be the derivative of R total over dr, and then the derivative of the resistance by conduction. This term in the denominator is all constant, so we can take that out. So it's going to be 1 over the thermal conductivity times 2 pi times the length. This is going to be multiplied by R1 over R2, and this is going to be using the product rule, like that. And eventually, I mean, these cancel out as well, but that's the derivative of the resistance by conduction. And then the derivative of the thermal resistance by convection. Again, we can factor out the constants. This is going to be 1 over the heat transfer coefficient times 2 pi times the length. And it's going to be multiplied by negative 1 over r squared. There we go. And this is going to be R2. I forgot to write that in there because convection is the transfer from a surface to a fluid. So where that comes in contact is at the end of R2. So that's going to be here. Oops. Says the radius 2 squared. So now we can set this whole thing equal to 0 because we're trying to solve for R2 to find what the critical point is of seeing how much insulation we can add. So now we can rewrite this to be 1 over the thermal conductivity times 2 pi times the length times 1 over radius 2 plus, I guess this would be a minus, 1 over the heat transfer coefficient times 2 pi times the length times 1 over radius 2 squared. This is equal to 0. And then we can factor out this 2 pi L and multiply it over, so those are going to cancel. So we're left with this here, 1 over the thermal conductivity times 1 over R2 minus 1 over the heat transfer coefficient times 1 over R2, or the radius 2 squared, is equal to 0. And now we're trying to solve for R2. So let's subtract this over. Okay, and then when we solve for R2, we're going to get that it's the thermal conductivity over the heat transfer coefficient. So the first derivative, when we solve for R2, this is going to tell us how much insulation we can add. But now we want to take the second derivative to see if this is the minimum amount of insulation or the maximum amount of insulation. So I'll just copy this down to here. And we want to take the second derivative of this. So this will be second derivative of the total thermal resistance over dr. Okay, so this one, these terms cancel before, so we can simplify that there as well. And so for the second derivative, we're going to end up with -1 over the thermal conductivity times R2 squared. And then we're going to add this to 2 over the heat transfer coefficient times R2 cubed. And then we just solved for R2, so we can plug this in there and there. So let's do that. So the second derivative of the total thermal resistance is going to be equal to -1 over the thermal conductivity times the thermal conductivity over the heat transfer coefficient squared plus 2 over the heat transfer coefficient times the thermal conductivity over the heat transfer coefficient cubed. Like that. And then we can simplify this a bit. We're going to end up with negative of the heat transfer coefficient squared over the thermal conductivity cubed. And then we're going to add this to 2 times the heat transfer coefficient squared over the thermal conductivity cubed. And we simplify this again, we're going to end up with a positive value. It's going to just be h squared over k cubed. And because it's positive, it's going to be a concave up term. So that means that this is going to be the minimum. So like the radius, this radius value is the minimum that it can be before the thermal conductivity starts to decrease. So let's show what this is looking like. So this is going to be the total resistance. And there's some point here, this is going to be the resistance by conduction, or the thermal resistance by conduction. And we just said that somewhere along here at R2, when R2 was equal to, we said it was the thermal conductivity over the heat transfer coefficient, we had a minimum. So it was a minimum curve like this. Okay, like that. And then that means that eventually, if we keep increasing the radius or the amount of insulation we have, eventually there's a critical point. I'll label that. Yes. And the more insulation you put, eventually the heat transfer, or the thermal resistance rather, will increase. But it is interesting that at R2, that's the minimum amount of heat transfer for this example. But the more you increase the insulation, once you get past the critical point, that'll only increase the amount of thermal resistance you have for the system. So this is going to be as R2 increases, which is just the insulation. And this is just showing that if you don't add enough insulation, you're going to be having less thermal resistance than if you just left the pipe bare as is, which is shown here because this is higher or having more thermal resistance up here than down here. So it's important to make sure that you're adding enough insulation and you know how to interpret this and what this means. So you're actually insulating your system and not doing it a disservice by not putting enough insulation on it for heat transfer.